Today, I am going to talk to you about the Blue Death and use it as a structure in understanding how early microbiology used the scientific process to determine that certain things were caused by or related to microbiological agents long before they actually had the capability of determining what those microbes were or being able to see them. So this is the Blue Death, and the story begins with Jon Snow. Oh, wait, not that Jon Snow. This Jon Snow. So Jon Snow was born in 1813 in York, England. He was a surgeon apothecary, and he became a surgeon apothecary through an apprenticeship starting at age 14. So instead of going to like a medical college, he started working with another surgeon apothecary, took some classes on the side, and pretty much dove right into doing varying kinds of microbiology work and medical work, working with some other practitioner of the time. He encountered Asiatic cholera in 1831 when he was only about 18, and he was sent to work with cholera patients. So cholera is what's called the Blue Death. Even though cholera is mainly a digestive disease that causes significant diarrhea, problems in the colon, it also throws off many other systems in the body, and death is often due to respiratory failure, so everything shuts down, including the respiratory system. Therefore, people had a blue tinge as they died. Okay. But here's the thing with treating cholera in 1831. The model that was being used to understand disease at this point in time is what was called the humoral model of disease. So physicians thought there were essentially four elements: this yellow bile, black bile, phlegm, and blood. And if these elements were all in balance, you had a healthy human being. If you had a diseased human being, one of these elements was out of balance and they were related to other things, how people felt, dry, wet, hot, cold, elements of the earth. There was a lot of misunderstanding in how all of this happened, and the humoral model of disease involved things like trying to balance the humors to cure disease. So it involved things like bloodletting with leeches as a disease cure, or emetics to force somebody to either vomit or force them into another state of diarrhea to balance out some kind of fluid. Or in some cases, they would add fluids to the system. So cholera, being seen as a loss of fluid, cold type of thing, was treated often with hot broth. The humoral model of disease at the time was what they had, but was it a model that made sense? Well, the scientists really would want to think a little bit about that. So if you were following the scientific process back in these days, what evidence could support or refute the humoral model of disease? So if cholera really was a dry, cold disease, and it was about misbalancing, then you should be able to counterbalance it. Then warm fluids should help balance it out. And although warm fluids probably were somewhat helpful to people, it certainly did not improve the rate of cholera death, which was significantly high, and so it was a problem. Bloodletting certainly did not treat cholera in any reasonable way. So although a number of these things were tried, most of what Jon Snow saw in treating cholera was that he couldn't do much. Most people got sick, many people still died, and he had some issues with this model of disease, as well as many other people, but it's always hard to knock the mainstream. So let's talk a little bit more about what was going on in London when cholera hit. So mid-19th century London did not have a sewer system. It had cesspools. Cesspools were often in basements or next to buildings, and it was where waste went. Human waste, cooking waste, wash waste, wastewater, all of it went into cesspools. And if the cesspools filled up, or there was an excess of fluid coming in from rainfall or something else, they could overflow into other places. Often overflowed water would end up in other what should be clean water systems. For example, the Thames, or the local large river that went through England, which, by the way, was also where people got their drinking water from. So there were companies that piped in drinking water, so you didn't have to live right next to the Thames or like track back and forth. But those pipes still came from many places that were varying levels of contaminated. So if you happen to have a company with an upstream pipeline, maybe your water was a little better than the companies with a downstream pipeline. You didn't always know where that was coming from. Now, because of this, There was a lot of stinky cesspools in Victorian England. It is not as pretty as they show it in most of the TV and movies. It was gross, it was stinky. And so this led to the miasma theory or model of disease, where, okay, well, if the humors aren't the problem must be coming from external, which is correct. But what people thought was that it must be caused by a toxic gas. If we can smell something icky, that something is likely to be causing disease. And so they connected it to the cesspools and said, well, we should drain out these cesspools so that we don't have any of these icky smells around. So this was probably better for cholera, and the outbreaks became less, but it wasn't perfect because the focus really was on just getting the stinky stuff out, often back into, again, the water systems. So if you dumped the cesspools into the Thames, but then still pumped water out of it, even though it looked like a lot of clean water was flowing through, it probably wasn't enough. They also were not as careful about less stinky water. So wash water and things like that might still have contamination while not being quite as awful smelling. But now, let's consider this new model of disease from a microbiological and scientific standpoint. Does this make sense? What evidence would support or refute the miasma model? Well, clearly, if smells are connected with disease, decreasing smells should decrease disease. And there was some of that. Again, if you got rid of the cesspools, there was some decrease in disease. But not entirely. There were definitely outbreaks of cholera in places that had been fixed of the smells. So that wasn't a perfect example. Another thing, of course, about the way a gas works is that it's up in the air, it's aerosolized, it spreads out. It should get everybody in an area. And cholera did not often hit that way. It would hit one household and not another, or even different members of the same household. So the miasma model is better than the humoral model, but it still seems to have some issues. And specifically, Jon Snow, still living through this and still interested in cholera, determined that it didn't really make sense based on what he knew. And he had become quite the scientist and experimenter because he was an early proponent of anesthesia. So a quick side trip to anesthesia. Anesthesia was not a thing in the early 1800s, and people started including it. So they would do surgeries without putting people to sleep or sedating them at all. And then they said, well, maybe in some cases we really need to because we can't have these people being awake while we try to make this whatever thing work. So they would take chloroform or ether, put it on a rag, and put it up against the person's face. Both of those are pretty toxic, so they'll sedate you for a while, but if you keep adding that toxic gas, it also killed people. Many women, in fact, related to childbirthing and other incidences were killed by ether and chloroform that were uncontrolled during those periods. So Jon Snow saw this and said, well, there's got to be a way to do it that makes sense. If it sedates them, but too much of it kills them, can we limit the amounts? And he started creating devices for administering the gases, had one of the earliest anesthesia practices, and is very interesting in this field. But this gave him a lot of information. He understood how experimentation worked. He had begun to publish papers in various areas. And he also understood how gases worked. And he really doubted the miasma theory of disease and began to suspect the causative agent was in the water. The animalcules, as people had been calling them, that had just been discovered. Van Leeuwenhoek was not that far before this, and there's not a whole lot of microscopy going on. He says there's got to be something in the water. That's what makes more sense. So, you are Jon Snow. What do? Well, you need to find evidence. People aren't going to believe you, again, without evidence, and he already knows the experimentation, so he needs to go out and find the way that water sources would relate to cholera. So, we already said that water came from different places in England. So one of the things that Jon Snow was able to do was, in fact, go looking for different water sources. Turns out not a lot of people knew where their water came from. They knew kind of what pumps they may have grabbed it from. They didn't know what companies pumped it in. There was a lot of uncertainty, but he did do some work nailing down cholera cases and finding maps in which he could connect the dots on things. So, for example, the blue here is one water company, the red here is another, and then there's some areas where they overlap and both companies have pipes. But there are some areas where they're next to each other in different ways. So you could try to find people with similar conditions, but different water sources, and compare their rates of cholera. Of course, cholera outbreaks went up and down, so they weren't always consistent. And so Jon Snow was being asked to essentially find a true experiment in which he could verify some of this data. And eventually, one fell in front of him. In 1854, there was a specific cholera outbreak in Broad Street, in which, when Snow went and interviewed households with cases, he determined they all got water from the Broad Street pump. So now he's got a fair amount of evidence that connects all of those things. But of course, it's not yet fully causative evidence. So what you really need to do at this point, if your hypothesis is the Broad Street pump is causing cholera, what do? Well, you shut down the Broad Street pump, which is in fact what he did. This is the Broad Street pump, actually probably a either replica or improved version of it. This is the John Snow Public House in England, so still there. All right, but he asked that the pump handle be removed. He managed to convince a local group that tried to help the lives of the poor in England, and they agreed that it couldn't harm anything, so they removed the pump handle, and the cholera cases went way down. So hey, that's pretty good experimentation. You have done something that changes the environment, and something changed in return. And it took a little while still to convince people. They were like, I'm still not sure about this. Cholera waxes and wanes. We're not entirely certain, but they did eventually excavate the pump site and revealed that there was contamination from a local cesspool with washing water. We're able to trace the cases back to sort of an initial starting point and really showed good evidence for cholera being from the water. And slowly, the acceptance of this model won out. Very slowly. Convincing the scientific world of something, even with good evidence, is sometimes very hard. But it convinced people enough and rapidly enough that they said, hey, we need to fix this problem. And a true sewer project was in fact constructed, and London was able to fix its outflow-inflow problems, and there really was no more cholera from that point on. John Snow did not get to see the end of this. He died at age 45 from a series of strokes, so he was not able to get to that point, but he did play a very important role. So you can see how even working microbiologically in a period of time when you couldn't even see or calculate or quantify any of the microbes that were there, the scientific process, understanding how to hypothesize, running experiments, and looking for evidence is important, and it can lead us to the tiny magical things that we can't exactly see using these broader scale concepts. So keep an eye out for that in other areas of microbiology. Hope you enjoyed that. Thank you.